So good morning to one and all. In computer vision and image processing, in first unit we discuss about the what I mean by image and what I mean by image processing, what I mean by digital image processing, and then what are the fundamental steps in a digital image processing. Then what are the components used for the image processing. Then what I mean by sampling and what I mean by quantization, how we convert the continuous image into the digital image. Then what are the relationship between pixels. So in relationship between the pixels, we discuss about the what I mean by connectivity, what I mean by adjacency, what I mean by region, what I mean by boundary, and how we can calculate the distance between the two pixels. We can discuss into each and everything. So the first one is a what I mean by image. So image is a simply we can define as a f of x comma y. So x comma y is a spatial coordinates, and then f is the function or amplitude of the particular pixel is called as an intensity or the gray level. So the image we can define as simply f of x comma y. So here the digital image processing is the processing of digital images in a digital computer. Then we can call it as a digital image processing. So then in digital image processing we have different types. One is a low level processing, middle level processing, and high level processing. So low level processing is nothing but so we can take the input as an image and output is also an image. And mid level, so we can take the input as an image, but the output is we try to extract some attributes from the digital image. Then next one is a high level. So high level is nothing but so simply we can take the input as an image, but the output is final output is the recognition of the particular object. So we can call it high level digital image processing. So simple definition of image is it is a consists of pixels, is a collection of pixels or the group of pixels. So the pixel we can define as the element of the digital image, we can call it pixel. The pixel is an element of a digital image. So now how we can image format model is here we can give as so simply we can see that. So here so I can use this pen. So here so f of x comma y, f of x comma y. So f of x comma y equal to I of x comma y into r of x comma y. So it is a simple image formation model. So f of x comma y is a intensity at the point of x comma y. So I is nothing but a illumination and r is nothing but a reflection. So illumination is nothing but how much light is grabs from the particular camera, and the second one is a reflection, how much is reflected from the particular object. You can call it a reflection. So the image you can formulated by using a illumination and reflection. We can represent it as I of x comma y and r of x comma y. So where I value is between 0 to infinity and r value is between 0 to 1. Here the illumination value is between 0 to infinity and the reflection value is between the 0 to 1. So next, suppose if you have take any image, the image we can represent as f of x comma y. So image can be represented as f of x comma y. Suppose if you want to perform any operation, suppose if you want to perform any arithmetic operation or any transformation operation, suppose if you want to doing any operation like resizing, scaling, all these are the different imaging operations. So if you want to doing any imaging operations on the particular image f of x comma y, so we can apply the transformation t. So in this we can see that. So here we can see that. So here we can see that. So this is f of t is a transformation function. We can apply on the input image. The input image is f of x comma y. So the output image we can represent as a g of x comma y. or we can domainly we can define as a g of x comma y and f of tx. So it is nothing but a elimination and so reflection, tx x comma y, ty x comma y. So simply if you want to perform any operation on the image, so f of x comma y is in your input image, the t is a transmission, is nothing but a operation we can apply on the particular image, though finally we get the output as a g of x comma y. So it is a simple image processing applying the operation on the particular input image. So these are the some fundamental steps in a digital image processing. So we have a totally these are the this diagram is represent the fundamental steps in a digital image processing. The first one is a image acquisition, image enhancement, image restoration, and color image processing, and wavelet and multi-resolution image processing, and compression and morphological image processing. The next one step is in a segmentation, then representation and description. The final one is a object recognition. So it is a all these steps are connected to the knowledge base. So the first step is a image acquisition. So the image acquisition is nothing but a, so we try to capture the image. Okay, so simply we try to capture the image. So in this image acquisition means we try to get the image from the camera. And here we can doing the some pre-processing. The pre-processing like a scaling and resizing operation we can perform in a image acquisition. So the next one is a image enhancement. So image enhancement is simply we try to alter your image, means we try to enhance the quality of your image, we try to improve the quality of the image. So suppose if you are doing the if you take the any input image, so I am trying to doing the enhancement. So enhancement operations like I am trying to increase the sharpness or the brightness of an image. All these are the image enhancement. So we try to improve the quality for better looking purpose. So the next one is a image restoration. So the image enhancement and restoration are these two are steps are interrelated. So one is a subjective and second one is a objective. So image restoration is a subjective criteria, means so image restoration is nothing but a, if you are captured one image, so the image is a degraded image. So due to some noise, the image may be degraded. So we try to restore the original image. Okay, so in the image restoration process. So the next one is a color image processing. So in color image processing we have a different color image processing is available. So RGB color image we can use the, basically we can use the RGB red, green and blue color image, or we can use a CMYK color image. So we try to doing the color images in digital computers, we can call it a color image processing. So the next one is a more wavelet and a multi-resolution processing. Wavelet and multi-resolution processing. So wavelet and multi-resolution processing is nothing but a, so we try to give the different dimension for your image. So we try to extract some components from your image. Okay, then we can call it a multi-resolution operations of the image. So the next one is a image compression. So image compression is nothing but a, suppose if you have take the image like a size of 256 by 256 or 512 by 512. So if you want to transfer the particular image to one network to another network or one system to another network, it takes more bandwidth. Okay, suppose if you take the satellite image, the satellite image size is a very high. So we try to reduce the size of the image without affecting the quality of an image. That purpose we can use the image compression. So image compression is nothing but we try to reduce the size of an image. Okay, so that's why when you transfer the image from the one network to another network, it takes the low memory or low bandwidth. Okay, so the next step is a morphological processing. The morphological image processing is nothing but a, so here we can apply the all morphological operations. So morphological operations, logical operations, arithmetic operations, so set operations. So we can apply the all image processing operation. So the main aim of the morphological image processing operations are we try to extract some elements from the the particular image. Suppose if you want to extract the boundary, if you want to extract the region of the particular image, so that purpose we can use the morphological image processing. So the best example of morphological image processing operations are the opening, closing, skeleton operation and arithmetic operations and relation operation, logical operations and set operations. All that comes under the morphological image operations. So the next step is a segmentation. The segmentation is nothing but suppose we try to divide the image into the different parts. Suppose if you take the human face, the human face is consists of different components like eyes and nose and tongue and teeth and hair and ears, nose and everything. So we try to interest on the particular portion of an image. Suppose if you take the satellite image, the satellite image covers the total area, but I want to know what are the resources available in the particular earth or the particular area, or what are the hill areas available in the particular area. So that's why we try to segregate or separate or segment the image into different parts, so for future enhancement of your image. So the next one is a image representation and description. So representation is nothing but simply we try to extract some components of the particular image after segmentation. So the components must be we can process by using a digital computer. So we try to convert the particular segments into the computer format. Then we call it as a representation. So representations are used to we try to, based on the representation, based on the particular segment, we try to give some description. Means simply we try to give some labels. The labels are used for recognizing the particular object in the last steps. Okay, so we can see that different steps. So these are the segmentation, and this is an object recognition and representation of this particular description. So all these key steps are the stages are in digital image processing. So the first one is a image acquisition, image enhancement. The next one is image restoration, color image processing, and wavelet and multi-resolution processing and compression. Then morphological image processing. Morphological image processing and segmentation, representation and description, and the final one is a object description. Okay, so this is all these are the key stages in a digital image processing. Okay, next the topic is components of digital image processing. So we can see this diagram. These are the components of your digital image processing. The first one is a image sensors. So next one is we can use the specialized image processing hardware and image processing software and hard copy and image displays and computers and mass device and the networks. So all these are we can call as components of the image processing. So the first one is a image sensor. So the sensors are used to capture the image. So the sensors consists of two devices. One is a physical device and the second one is a digitizer. So the physical device is used to we try to capture the image. So image capture you try to capture the image. The image is in a continuous form. So we try to convert into the digital form. So for that purpose we can use the digitizer. Okay. So in this particular image sensor we can use the two components. One is a physical device and the second one is a digitizer. Okay, digitizer used to convert your image into the digital format. So the next one is a digital special image processing hardware. So special image processing hardware consists of digitizer plus some hardware components. So we try to perform the all logical operations and arithmetic operations and logical operations, everything. So we can use the specialized hardware components. So the next one is in a computer. So the computer is an image processing system. So based on your application, so we can use the different types of computers. So like a normal PC to the supercomputers. Suppose if you want to doing the normal image processing is nothing but like a Photoshop. So we can use the normal computer is enough. Suppose if you are using the satellite images. So satellite images, if you want to process the satellite images, we need the extra hardware components at the same time. So the supercomputers are used for the analyzing your satellite images. So the next one is a software. The software is nothing but if you want to process the particular image. So suppose if you take the Photoshop, so you try to increase the brightness. So we have a small button like a brightness button. If you click on the brightness, automatically it increase the brightness of the particular image. So the software is a collection of the packages. We have a different packages available. So based on your requirement, we can choose the package for enhance your image. Okay, the software is a consists of the different packages. So the package, suppose if you want to enhance the image or rescaling the image, so predefined package is available. You just know how to write any code. So using the particular softwares, and we try to enhance the image. So the next one is a mass storage. So mass storage is nothing but after completion of manipulation of your image, we try to store your data. So that purpose we can use the hard disk as your mass storage. So in mass storage we have a short-term storage and online storage and archive storage. So short-term storage is nothing but simply recurrent. We can use the rapidly used images are used in a short-term images, and online storage so used on the magnetic disk and optical medias, and archived storage is a optical disks and magnet tapes are used. But if you are using the archive storage for the rare usage of the particular images. So the next one is a hard copy. Hard copy is nothing but we try to use some printer for the, so after manipulation the image we try to take the printouts. So that purpose we can use the hard copies. So then next we can use the image displays. So image displays is nothing but we try to display the image by using a monitors or LCD screens or anything. So we try to convert after completion of the manipulation on the particular image. So using this network, so we try to transfer from the one place to another place by using this network. Okay, so these are the components of the image processing. Simply, so image sensor, it consists of two devices, image physical device, and the next one is digitizer. So we can use the special software, hardware and software for manipulating the image, and we store the image by using a mass storage. For displaying the purpose we can use the LCD screens or normal TV screens, and a hard copy is nothing but we try to simply take the print of the particular image. So these are the components of your image processing. So these are some description about the components. So image sensors, image hardware processor, and computer, image processing software, mass storage, and the networks. So the next one is the next topic is image sampling and quantization. So the sampling and quantization is nothing but simply the sampling is nothing but we already discussed about the image is so image we can also discuss about the image is so f of, so image is f of x comma y. So image is f of x comma y. So here x comma y is a spatial coordinates. So the next one is f is simply we can call as intensity of the particular image. So we can see that here we can take the one image. So we can take the one image. I can draw the one line here, A to B, the scan line. Okay. So the sampling is nothing but the digitation of your coordinates, xy coordinates distances we can call as a sampling. So the quantization is nothing but convert into the amplitude values into a digitization form. The sampling is nothing but a digitation of coordinates. Okay, values is called as a sampling, and digitation of the amplitude values is called as a quantization. So we can see that image. So this is now an image, and we try to draw the one scan line from A to B. So here scanning line from A to B. So I can take the all intensity values in this A to B. So we try to draw the intensity values here. So these are the one pixel from here to here. All the pixel intensity values is like this. So this is I am trying to take the samples. The squares are we can call as samples. So we can take the samples on a total scan line from the A to B. So after taking these scan lines, we try to digitize the values here. So these are the digitized values of the digitized diagram of this D. So this is the digitization scan line of this particular A to B. Okay. So the sampling is nothing but the digitization coordinate values. Okay, is called as a sampling, and digitization of the amplitude values is called as a quantization. So this is an image, continuous image. After digitization, we can see that image like that. Okay. So if you want to represent the particular image, So image may be in a size like a n by m or n by n. N by n is nothing but a, suppose if you are take the image like a 256 by 256. So 256 by 256 is nothing but a, so the m and n values are equal and n by n image is called as an n square. So m cross n is nothing but a, m value is a 128 and n value is a 256. So we can take the different dimensions, m and is a and n the different dimensions. So simply we can represent the image f of x comma in different ways. So f of 0 0, f of 0 1, so f of 0 n minus 1, and this is the f of m minus 1 to 0. So it is a simple representation of your image. So then we can represent the numerical array. So array representation of the particular image is a, so the first coordinate we can take it as a0 0, so the next values we can take it as a0 1, and here the first column last row we can take it as a m minus 1 to 0, and the last column last row we can represent as a of m minus n, n minus n. Okay, the next one representation of the particular array in a MATLAB we can use f of 1 comma 1, f of 1 2 comma, so this is f of n, f of m comma n. So you can use the matrix representation for the particular image. So suppose if you take the one image, the image size is a m cross n. So how many bits are required for storing this particular image? So image size is a m by n. Then how we can use this? I want to store this image m cross m image. And for storing this m cross n, how many bits are required? So here the b is a number of bits required for storing the image m cross n. So here the formula is b equal to m into n into k. Okay, m into n into k. So m and are the dimensions of your image. The k is nothing but the levels, number of gray levels in the particular image. So l is nothing but a 2 power k. Suppose if you are taking the grayscale image, the grayscale image consists of 0 to 256 values. So means maximum is that 247 values is available. So I can show that this is in a table. Suppose if you are using the level 2, level 4, level 8, level 16 means, so 5-bit representation, 6-bit representation, 7-bit representation, 8-bit representation. Suppose image size is a 32 by 32. So 32 by 32, and I am trying to store in a level 8, so it's nothing but a 3-bit level, 3 bits. So it takes the number of bits is a 3072 bits. Suppose if you take the 1024, so the n value is a 1024 by 1024 image. Suppose if you want to represent the, so 3-bit representation for the particular image, so here 314572 is a, so the number of bits required for the particular image. Okay, so this n is nothing but a dimension value. So this is the number of bits is required for the storing the particular image. So all these are the bits are required for the particular image based on the size of or dimensions of the image. So the next topic is the base-scale relationship between the pixels. So in base-scale relationship between the pixels, so we discuss about the neighbors, adjacents, connectivity, and paths and regions and boundaries. So suppose if you take the one image, so image the origin is a, we can call it a p of x comma y. So the origin of image or center point of the pixel is a p of x comma y. So suppose if you can, this is a pixel, so we can take the any pixel p of x comma y. So there is a, so top and bottom values and a left and right values. Suppose if this is a p comma x comma y, then here the value is a x plus y and y. So then this value is a x minus n 1 and y. So top value is a x comma y minus 1 and a x comma y plus 1. So 1, 2, 3, 4. So if you take the pixel p, there is a 1, 2, 3 at both top and bottom and left and right. So we can call as a horizontal vertical neighbors. So then is called as a 4 neighbors of a pixel. So the 4 neighbors of pixels is nothing but a, we can represent as a n4 of p. So n4 of p is nothing but a, we can consider the both top, bottom, left and right values. Okay, so then we can consider the diagonal values. In previous we can consider the horizontal and vertical. So now we can consider the diagonal values. Suppose if you take the p x comma y. So in p x comma y we have a, this is a one diagonal, it is another diagonal, it is another diagonal, it is another diagonal. So now the diagonal values are, this diagonal value is x plus 1 and y plus 1. Suppose this is a p of x comma y. then the diagonal of this one is a x plus 1 y minus 1. So the diagonal of this one is x minus 1 y plus 1. So this is an x minus 1 y minus 1. Simply we can add the one unit and subtract the one unit from the particular distance of this particular pixel. So this is called as diagonal of the particular pixel we can represent as a nd of p. So n4 of p is nothing but a 4 neighbors, nd of p is nothing but a diagonal of p. So the combination of both diagonal values and top left and vertical and horizontal values, then we can call as 8 neighbors of a pixel. So you can see that here 8 neighbors of the pixel, p is denoted as a n8 of p. n8 of p is nothing but it's a combination of both 4 neighbors and diagonal neighbors. So n8 of p. So the next one is adjacents. So adjacents lo we have discussed about the 4 adjacents and 8 adjacents and m adjacents. So the 2 pixels p and q with a value of from v are the 4 adjacents if q is in the set of p. Suppose if you take the 2 pixel p comma q. Okay, so if p comma q, when you said that it is in a 4 adjacents, the q value is there in a n4 of p. 4 neighbors, so the p value must be there. And 8 adjacents is nothing but if 2 pixel p and q with the values from the v are 8 adjacents if q is in a set of n of p. So n of p is nothing but we can consider the both neighbors and diagonal values. So if you take the q is there in for 4 points we can call as an 8 adjacency. So m adjacency is nothing but a combination of 4 adjacency and 8 adjacency. Okay. So this is the particular definition for m adjacency. If 2 pixel p and q with the values from the v is in a set of values. So if must be satisfy the 2 conditions. The first condition is a q is in a n4 of p or q is in a nd of p, and the set of n4 of p intersection n4 of q is a no pixel and whose values are from the v. So no intersection point between the 4 pixels. Then this called as an m adjacency. Okay. So next you can see that this one. So these are the one image. The image is a binary image. The pixels is 0, 1, 1, 0, 1, 0, 0, 0, 1. Okay. Then the pixels of 8 neighbors. So this is a, suppose if you take this as a p, if you can consider as a p, so we can consider this as a top. So it is in a diagonal, it is in another diagonal. So all these are the connections. Suppose if you are m adjacency. So m adjacency, based on the definition of the m adjacency, the n4 of p and n4 of q is not a intersect value. So that's why, so this connection is removed. So in m adjacency, this connection is not available. So this is an 8 adjacency, it is an m adjacency. So based on the definition of the m adjacency, the n4 p of intersection n4 of q, so it is an empty set. So that's why this is a removed. Okay, so these are the examples of the p adjacency and this is an m adjacency. So the next one is a path. So path is nothing but suppose if you take the 2 pixel p and q. So the p and q is connected via so many intermediate pixels. Okay, suppose you can consider the p is a coordinate x comma y and the q is a coordinate x comma t. Suppose p and q. So p is connected to the q with the intermediate pixels. So in intermediate we have so many pixels. Okay, it may be 1 or 2 or 3 or 4. Okay, suppose if x naught y naught equal to x and y, then it's called as a closed loop. So simply can form the loop. So it's nothing but a cycle. So we can suppose if you can, this is p, it is in a q. So it is in a path from here and here to here. So here this is in a p, it is in a q. So there is a path from this one and this one. So if you take this is a p, it is in a q. There is a path from p into q. So by using a m adjacency or 8 adjacency. So next region and boundary. So the region is simply we can call as an R is in a subset of the pixels in image. So R is a region of the image is a connected set. And the boundary is a border. Boundaries you can also call as a border of a region R is a set of pixels in the region that have a one or more neighbors that are not in a R. Okay, then we can call as a boundary. Suppose the R is in a set of pixel, so the pixel is there in a R, we can call as in a region. It is not there, then we call as in a boundary R. So next we try to calculate the distance between the two pixels. So we can take the 3 pixels here, P, Q, Z with the coordinates x comma y. So x comma y is a coordinate of the pixel P, and S is a coordinates of the Q, and Z coordinates are the U, V comma W. Suppose if you want to calculate the distance, so we can distance conditions are, so if P comma Q, distance of P comma Q greater than equal to 0, or if P equal to Q. So if the P or the Q are the same pixel, then so the distance is a 0. So if the second condition is a D, the distance of P comma Q equal to distance of Q comma P. So P to Q and Q to P have distance is same. And the second one, suppose if you want to calculate the distance between the P to Z, the distance of P to Z, so this is a P to Z is less than or equal to distance of P comma Q plus distance of Q comma Z. So the next, the distance measured we can differentiate the different ways. So if you already know the equivalent distance, so if you want to calculate the distance from P Q, so P is a x comma y and Q is a x comma s comma t. So now the distance, equivalent distance, we can represent this formula s minus x whole square plus y minus t whole square the root over. So it is an equivalent distance formula between the two pixels. So the next one is a D4 distance, is called as a city block distance. So this is called as a city block distance, D4 distance. We try to calculate the distance between the 4 neighbors. Okay, so D4 of P is given as a, so modulo of x comma x minus y plus y minus t. So here the D4 is distance from the x comma y is less than or equal to the some value r from the diamond center of x comma y. Diamond center is nothing but the origin. So here the P and Q, so we try to calculate the distance from the D4. So this distance is called as a city block distance. The formula for calculating the city block distance is a x minus y plus y minus t. So the next one is if you want to calculate the, suppose this is a 0, so this we can consider the neighbors only. So left and right and top and bottom. So we can consider this one. So the unit distance, it is a 1 unit distance, it is a 1 unit distance. Suppose if you want to go to this one, so 0 to 1, 1 to 2. Suppose if you want to go to here, so 0 to 1 and 1 to 2. 0 to 1, 1 to 2. Suppose if you want to go to here, this pixel, so 0 to 1 and 1 to 2. Okay, so you can consider the only 1 unit of distance between the pixels. So the next one is a chessboard distance. So it is called as a D8 distance. So D8 distance we can represent as the maximum of x minus y and y minus t. Okay, so you can take the distance from here and here. So we can take the maximum value between these particular pixels. So this is a city block distance. So we can consider all the neighbors and diagonals here. 0. So neighbors, diagonals are 1. Suppose if you want to travel here, so 0 to 1 and 1 to 2. Suppose if you want to travel here, 0 to 1 and 1 to 2. So it is called as a city block distance. So we can, if you want to calculate the distance, is a P, P1, P2, P3, P4 are the some pixels. So the P1, P3, P, P2, P4, P, P2, P4 values are 1 and P1, P3 values are 0. So then we have a different case. Suppose these are P1, P3 values are 0. We try to calculate the distance from P to P4. So P, P2, P4, P, P2, P4, all the ones are connected here. Okay, suppose if you take the second case, so P1 value is 1, P3 value is a 0. Then we have to connect it P, P1, P2 and P4. Okay, so the zeros are eliminated, only ones are connected. The next one is the next case is a P1 is 0, P3 is a 1. So now we have to calculate the P, P2, P3 and P4. So it is a distance measurement of your different pixel between the P and Q. Okay, so we can take the all values are ones. So you take the all values are ones means, so P, P1, P2, P3, P4 and P4, the distance is a increases now. Okay, so now in this class we discuss about the what do you mean by image and what do you mean by digital image and what are the fundamental steps in a digital image processing and and then we discussed about the components of digital image processing and sampleization and quantization. Finally we discussed about the relation between the pixels. So in adjacency, connectivity, path, region, boundary and distance, everything. Okay, so it is a recording of the first unit. So thank you very much.